Hi guys, I forgot a very small point. In the VCO design, there is there is a third way, which is nothing but controlling the voltage. So essentially what you do in that approach is you can just take the three-stage ring oscillator and you can vary this node voltage. By varying this node voltage, what you do is you are changing the overdrive strength of this device, or rather current charging available for, the available current to charge the capacitor at this node. So for example, if I increase this node voltage, your current, the overdrive required for the available for this device increases. So the current charging this capacitance increases, so your frequency will also increase. So this is the third approach. So normally what we do is we connect a big resistor, not a resistor like this, a resistor of value R, and then change your voltage at this point. Okay, so when you change the voltage, what happens is this is a low impedance node. Normally this node what we do is we connect a constant current source here and then vary the node voltage, and this, if you increase this node voltage, there will be more current flowing in the circuit. Reduce this node voltage, current will be drawn into the circuit. Okay, so this is the third way, by using voltage control. So you can directly control the voltage, which will in turn directly control the current into the oscillator. But if you see this approach, the current has to be provided by the voltage input. If you had seen, for example, using a capacitor tuning or a current tuning using a MOS device, you just converted V tune to a current and then used a current mirror and all that, okay, to feed it to a VCO. We just had a current mirror, right? If you remember that, we just had a PMOS based current mirror. That is other circuit. Even then, no, there was no current drawn from V tune. Even here, there's a capacitor, there is no DC current drawn from V tune. But in this circuit, as you change your voltage, V tune voltage, you will have to provide some extra current into this device. So that's the normal problem. So that is why if you want to use this voltage control, normally what you do is, normally your loop filter is a passive loop filter. A passive loop filter can't provide current. So we normally insert a buffer, a voltage buffer, and then connect a resistor and a set of inverters like this, we just connect a set of inverters like this, and this will be your circuit. Okay, so this is the third approach of doing it. You can try this one as well. As I said, whoever tries more innovative ways of frequency tuning, the marking grading will be done accordingly. Okay, if someone chooses a risky architecture, I'm fine with that. If you have provided understood that, we will grade you accordingly. Or you can choose the safer ones, current tuning using just a current source, a simpler voltage to current tuning conversion, it's fine. Even this will work. The only thing is you'll have to insert a buffer in between so that you can provide for the current. Okay, I just missed this out, so I just wanted to explain it. So you can ask me, why do you have to put a resistor? I might as well directly, connect a voltage here and then tweak it. So what happens is, it turns out normally in normal ring oscillator architectures that we encounter in practice, the kV that you can obtain by directly tuning the supply, the voltage, will be pretty high, will be of the order of gigahertz per volt. So for you to get off the order of 0.2 gigahertz or 200 megahertz and 100 megahertz or 50 megahertz per volt, you normally use a resistor instead. So even if I change this node voltage by delta V, the looking down impedance usually is very small. Let me call it Rn is the looking in impedance. Then the change at this node voltage is going to be Rn by Rn plus R. So even if you change this node voltage by large value, the change in this node will be very small. So your frequency change, let's say for the gain at this point is 2 gigahertz per volt. I'm just giving an example. Let's assume it's 2 gigahertz per volt, which means if I change this node voltage by 1 volt, the change in frequency is 2 gigahertz. But if I want a 200 megahertz change, I should change this node voltage only by 0.1 volts. Okay, so I'll insert a resistor here such that this ratio is going to be 0.1. So if this node voltage goes by, this control voltage, tuning voltage goes by 1 volt, then the node at this node, the node at which is the common source node for all the PMOS devices shown here, will vary by 0.1 volt. So frequency will change 0.1 into 2 gigahertz per volt. The frequency change is going to be 200 megahertz. Okay, so that's other intelligent way of designing it. I just wanted to, I missed out this in the previous lecture, so I just wanted to cover it now.